All right, I hope to live up to the promise here. I'm Chris, and this is a talk about trusted types. Let's start. Imagine what if we could fix the root cause of DOM XSS, like completely. What if we could at the same time help the developers to write secure code? What if we could simplify significantly the security reviews of such code? And doing all of that didn't require breaking or rewriting your application from scratch. That would be cool, no? And this is exactly what I will present. So first, a very short refresher on DOM XSS. I imagine most of you are familiar with it, so we'll just skip right through it. DOM XSS is a purely client-side cross-site scripting variant. So the entirety of the vulnerability lies in the JavaScript code running in your browser. It starts from a data being read from an attacker-controlled source, then being passed around throughout your JavaScript code down to something that is called a DOM XSS sink. So an attacker-controlled source, usually like a classical one, is the location hash object in your JavaScript program. And later on, this gets outputted without proper sanitization, for example, into the inner HTML property assignment of any HTML element, right? Classic, DOM XSS 101. Why do we still have it, though? We think that it's because of two separate reasons. First of all, DOM XSS is extremely easy to introduce when writing web applications. And second of all, it's super hard to detect it or prevent it or find it or spot it. Why is that? DOM API is, from a security perspective, a super terrible, badly designed mess. And you can see that very easily. Like very first JavaScript program that you write probably will create a DOM XSS vulnerability as long as you process any user input. The thing is, I've already mentioned inner HTML being a DOM XSS sink. There's like over 60 properties or functions available to the browser that are able to do just that. Like take a string and then make it cause a JavaScript execution controlled through that string, let's say. Eval is a classical example again. It takes a JavaScript snippet and it will just execute it. But there's others like inner HTML, source property of the script element, insert adjacent HTML property of any element, and the second parameter here is HTML, so it gets more complex. You could also parse from string using the DOM parser object. There's window open, and there's like over 60 things. All of them have one thing in common. They accept either a URL, an HTML snippet, or strictly a JavaScript code as a string, and then they just will, process it in a way that will cause JavaScript execution. On the second thing, why DOM XSS still exists, it's extremely hard to analyze JavaScript code, especially in terms of DOM XSS. It's hard to spot the actual vulnerability. In practice, what happens is you do not have like the reading from source and assigning to the sink right next to each other. There will be like a huge cold stack of functions in between them. Therefore, to find out whether you actually have a vulnerability, you need to start usually from a sink and then go up the chain, analyzing the program and seeing whether the sink was actually assigned something that was user controllable, right? Whether there was a link between the source and the sink. And that gets hard because JavaScript is a dynamic language. It's not something that you can analyze statically very easily. There are projects around that, and there are subsets of JavaScript that allow you for that, but this is not very practical or adopted widely. So here there are a few examples of why this becomes difficult, right? I don't know if this is a DOM XSS vulnerability. It depends on where the bar comes from. I don't know whether this is just looking at this line of code. I don't even know that this is a sink assignment. It actually is, because once you get into this property name function and some condition matches, that actually is an assignment to HTML, and so on and so forth. There's a lot of wrappers. And DOM XSS happens because the developers get to work with this ugly, messy API, and inadvertently they do introduce DOM XSS over and over again. And it's not their fault, it's the fault of the API. And it's also a growing problem. it's a growing problem because our JavaScript code size just simply grows. Our applications tend to get bigger on the client and not smaller. So your immediate code of your actual application gets exposed to this messy API, but the very same functions can be called by one of your dependencies, the ones that you load as part of your build chain. But also the scripts that are being loaded at runtime have access to the very same DOM API and also can trigger the vulnerability. So it grows and grows and explodes. The problem becomes untenable. We think it's untenable for especially a beginner developer or a developer who handles a complex application to write a code that is DOM XSS free. At Google, as a consequence, we already know that DOM XSS is by far the most popular variant of the XSSs that we get reported and fixed. So it is a problem. It is a real-world problem. Thankfully, we also do know how to address it. In Google, since a couple of years, we use the approach that is called safe types. It protects virtually all of our, let's say, core applications, like so Google Docs, Gmail, all of that. We have an evidence of efficacy of this solution. This solution focuses on being able, or giving the developers an API that enables safely producing a given values, even from the user input. And later on, those values can safely be propagated throughout your code base and then assigned to DOM sinks. It's implemented as a library in various programming languages, but still we do suffer from occasionally from the DOM XSSs. The reason why this is happening is that when we try to evaluate the program, or when we try to reason about its security, where we try to protect it, is when we compile the application. We actually, at Google, we also compile JavaScript. So, and that seems fine. Unfortunately, the very same program runs at runtime. And here, some of the assumptions that we have made when compiling actually do not hold true. Like, for example, there's an additional library that the developer just included without going through the compiler, right? It just happens, especially at scale. So trusted types is a way of moving that solution that we know works to the browsers, such that we can have the very same guarantees at runtime, and such that not only Google can benefit from it, but the whole community that writes the JavaScript programs nowadays. And with that, we can, I think, practically solve the DOM XSS problem. That brings us to trusted types. This is the solution that we will be describing here. Yeah. Yes. So what are trusted types? That's not a good question. Why are trusted types is a better one. So we want trusted types, the API, to adhere to certain design principles. They are really important for us. So first of all, we want trusted types to empower the developers such that they have a chance of writing secure code easily. That becomes like this natural thing. Like you start adding code and that it's secure because it's the most natural thing for you to do. We want to move to the secure by default APIs. We want the developers to get the feedback that they are doing something risky or wrong as early as possible. So we're pushing left again. So for example, as you are typing the code, we can give you suggestions saying, well, you are just introducing maybe DOM XSS, use this other function instead, for example, right? At the very same time, we want to empower the security professionals such that they can control the security relevant code of the application. They do not need to look at the entirety of the code base. They only need to look and review and protect changes to those critical small amounts of code that only those are security relevant, at least in terms of the DOM XSS exposure. So with trusted types enable us to do that. And at the very same time, we want to integrate with the existing ecosystem. So we want to leverage what's good, work with something that already works, be backwards compatible, allow the gradual migration, all that. Let's not just break the applications and by throwing out the DOM API and saying you need to use something else completely. Sorry. So the main idea of trusted types is we stop using strings as the value type. We no longer pass them to the DOM strings directly. What we do instead is we use objects, JavaScript objects. The good thing is that the DOM API actually already supports it, it always had. Here's an example. If you assign to an inner HTML an object that has a toString function that returns some value, the DOM API will just try to stringify this object, so call this function implicitly, and then the result value will be actually assigned to the DOM. So we can already start using objects in our JavaScript programs without breaking the functionality of the applications. However, there's a couple of more things that we need to implement. Instead of using plain JavaScript objects, we use typed objects. So we create a couple of classes, if you will, that represent different types of values that we expect to be propagated throughout the program flow. So there's a trusted HTML type, which represents a snippet of HTML that our application trusts to be okay to insert into the DOM. We also have a trusted script type, which means a snippet of JavaScript that is okay to execute. A trusted URL, which is something that you can safely link to, and the trusted script URL is something that you can link to that will load the JavaScript and execute, like a script source. And with those components, those primitives, the only security critical part is we can make the DOM API behave slightly differently. Make it just reject a string variant and only accept those typed objects. That's the whole trick of trusted types. So sorry, we're done.
What if I have a string, like a username I want to add? What if I want a simple string type that I do need to enter that?
Do you want to add it in a way that could potentially cause the JavaScript execution?
No.
So you don't need to use the types in this regard at all. Like for example, if you want to assign to an inner text property, you can use a string because that one has no DOM XSS risk. So only if you want to assign to a script source, for example, you would need to produce a value that's of a given type. All right, how does it look? Let's look at some code, right? How does it look in production? So you can enable the enforcement of the type, so you can make this switch of the DOM API by using the content security policy header with the trusted types directive. This star, ignore for now, we'll get to that. And once, of course, in a supporting browser, once this happens, the DOM will stop accepting stringed objects for given sensitive functions, and will just throw a type error. Like, you're doing something wrong. I don't want strings here. They potentially are attacker controlled. However, you can accept, or the DOM will accept, a trusted type object. What this one allows us to do is also we can just trigger the report only mode, which is pretty good for adopting any security solution. So I can still accept a string, but I will report it to some endpoint, right? We're using the regular CSP infrastructure. We're not rebuilding something from scratch. We're not reinventing the wheel. And the typed objects obviously do not cause any violation. No reporting is being done for them. We can also have no enforcement, like if you have a completely invalid CSP header or there's no CSP header whatsoever, your application continues to work. That's the surprise. You can use a string, sure, it accepts, so it's potentially vulnerable, but also it doesn't break because if you use the types, it's just backwards compatible. That's a very good boon for adoption, let's say. Now, how do we create the types? Now, this is a tricky part. You don't just create the types directly by just calling a constructor function. No, that would be pretty bad. We need more abstraction. So we allow the developers, or we allow the JavaScript program to create a set of policies. And a policy is just a JavaScript function in the end. So you create a policy using this trusted types create policy function. And what do? First of all, you give it a name. And this policy from now on will be identified by a name or controlled by a name. We'll get to that later. And this policy defines a set of rules that will be run whenever someone is trying to use that policy to create a trusted type object. In this particular case, if a developer wants to use this sanitizing policy here, create HTML function, passing it whatever, it can be user-controlled data, that user-controlled data will be passed through your custom sanitization rules, like it can be DOM Purify, for example, and the result value from this one will actually be wrapped into this trusted HTML object, which then you can safely use with the DOM. Yes? Line 3, where? Here? Sorry. I didn't compile the code example, sorry. And there's this extra part, because not always you can control actually the entirety of your code base. So we have something that is called a default policy. So you can create in your application a single policy called default, and then it has its own rules. That policy will be called as a fallback mechanism anytime you actually have called the DOM sync with a string. So it allows you to recover, sanitize something at the very end, or optionally, log something, report something. You can implement any custom logic you want here, such that it helps you migrate towards trusted types. So first of all, you can have coverage for separate parts of your application, but the remaining parts will be covered by this default policy. Yep. Demo. Jim tweeted a couple of days ago, like, we know how to fix XSS. Let's just make, inner HTML, just sanitize. You're wrong, Jim. This won't fix the DOM XSS. Nevertheless, this is trivial to implement in trusted types. So let me just present you how. Yep. So this is an application, a very simple toy application. We have an input field here, and we have an output field here. And there's 2 buttons. If I press this button, that data will be sanitized with DOM Purify and outputted here. With this one, I will just use the direct inner HTML assignment, right? So we all know what will happen. Here, the inline event handler will be removed, and it's all fine. However, when I press this one, we have an XSS. However, let's see what happens once we enforce the trusted types. And what we do right here is what happened. We added like this content security policy header with those additional values. I will get to what those values means in a second. But if I sanitize the value, I will route this data through this DOM Purify. It's inserted into the DOM. However, if I try to insert it directly using a string, something is wrong. Like I have a type error here. Something is wrong. What does it mean? Like there's an inner HTML and then like whatever. I read something from the DOM and that's a no-no. So the application breaks in the sense that functionality breaks, but we also do not have XSS. So that's pretty cool. Now here comes a question like, wait, how does this one work? Like, how come the sanitization is magic here? Well, the magic comes from DOM Purify itself. It supports trusted types. So DOM Purify creates its own policy, and after the sanitization, it will just will give you the trusted HTML object back that contains the sanitized code, and in the end, you can just directly use it in your application. No changes required from your end. You just use the libraries that are trusted types compliant, and you're good to go. Now, let's install the default policy. This is the experiment that Jim wanted. This is the web that you want, Jim. The default policy, we'll just actually see it in action. So I press the inner HTML button. The default policy helpfully has this debugger call, so I can show you what's going on here. The default policy will just has a create HTML function. This is the input to it. And it just decides to sanitize anyway because sanitization everywhere is okay, right? So we're sanitizing everywhere. We're just going through, and this is the output value. This is the default policy in action. Now, our application has this header here, right? Trusted types, DOM Purify default. What does it mean? That means that we enable the enforcement of the trusted types, but I only allow those 2 policies, DOM Purify and the default. Let's see what happens if I try to install a custom policy. Well, this policy has a name that is not on a whitelist, and it just fails. There's a type error. You cannot create a policy that the application owner, let's say, didn't allow you to. So that brings us back to the next slide. What I've demonstrated right here is that you have a tight control over the policies. First of all, you can control the policy creation. There's this whitelist in the CSP header in the Trusted Types Directive, meaning that none of your dependencies can create the policies that you didn't allow for before, right? So there's no code changing under you that can suddenly create trusted types and therefore expose your application to the DOM XSS risks. So all the policies on your whitelist are somehow known to you. You control them, you have reviewed them, you've looked at it. There are no drive-by policies. And obviously, as a consequence, you cannot actually create the policy with the same name twice. The second call will simply break. So even if someone tries to be sneaky and tries to create a or piggyback on a policy, this call will fail. But the actual important additional control that you have is you can control the policy usage. Policy, again, embodies the rules that are being run whenever a string is being converted to a trusted type. And there can be many policies. Some of them are more strict, some of them maybe are more relaxed. Some of them you have reviewed, some of them were introduced by one of your dependencies, for example, right? But policies are JavaScript objects. Therefore, you can control access to them using the regular JavaScript programming language features. So you can lock them down in a single module, you can create a private class variable, you can wrap them into a local function variable. So you not only get control over which policies can be created, but what gets exposed, what gets access to separate policies. Let's see an example. There's a policy that clearly is unsafe, right? It just takes any value with no sanitization and returns the same thing. However, we can argue that this code doesn't cause XSSs easily. Even statically, we can analyze that, because this policy never leaks outside of this function body, and this function body only is using it in this particular thing that doesn't contain any XSS whatsoever. It's just some part of template rendering of your application, for example, or template management. So this is an additional control that we can add to our JavaScript programs, such that we can compartmentalize the modules within our applications and give broader access to the policies that are sanitizing, and much stricter access or much locked down access to the policies which are, more risky, let's say. What benefits does it bring us? First of all, we have a much dramatically reduced attack surface for the applications. What previously used to be those 60 functions, and any time a string was passed and the string was attacker controlled, we had an XSS. Now, every risky data flow has to necessarily go through the policy, right? First, you need to read something from a source, then something happens, then a policy object gets created, then used, and the policy applies its rules, trusted types object is created, and only that trusted type object can later on be passed into a sink. So this is a critical piece in the whole chain. This is the thing that you have to review. This is the thing that you have to control, and this is the thing that you can put controls over. It does follow that if your policies are secure, that your application doesn't have the DOM XSS. And that's a very critical thing for trusted types. Very good, big advantage here. If you do not have access to the policy object, you cannot introduce a DOM XSS. So if you're using a library that maybe talks to the DOM, maybe it doesn't, you don't know, you don't really even want to review it because it's just like a blob of JavaScript that does something and there's 300 of them, so you need to cut corners somewhere. Just don't give it access to the policy object and see what happens. Does it break? If it doesn't, then it never needed to talk to the DOM and you're done. So it dramatically minimizes the trusted code base that is security relevant for DOM XSS at least. And with that, simplifies the code reviews. But there's more. This API is strongly typed, meaning that our JavaScript code is easier to inspect statically. We can reason about the code in an automatic fashion. We can enable the code completion, the linter checks, the documentation around it, automatic refactoring even. And the security validation, of course, happens at runtime because it's a browser API. But now also we can push this left to the compiler level. We can assert that a certain function is being called with a type. That's also backwards compatible because you can start using trusted types in the application without enforcing, and it will be stringified by the way the DOM API already behaves, and it does complement other security solutions. Like, for example, trusted types cannot do a thing for server-side XSSs. It's completely the wrong choice for that. So if you have a trivial, say, PHP application and you just output something without escaping from the get parameter, like trusted types won't help you at all. What can help you here is, for example, a nonce-based CSP, right? So you can embed trusted types in your already in your existing solutions for XSSs. Let's see some demo. All right, so this was a toy application, but now let's look at something more serious, let's say, right? So we have an application that is called the Cloud Player. It's an open source application built on top of the Angular framework, and we decided to port it to trusted types. So because it is based on the Angular framework, that makes the job quite easy. The way the Angular applications are written is most of the writing to the DOM actually happens through the framework by the engine that does the interpolation of the values into the Angular templates. And Angular already has a concept of sanitization. It has a lot of security in regards to DOM XSS embedded into it. And that makes Angular a very natural customer or producer of types. So what we need to do to enable our Angular application to use the trusted types, or at least as a first stepping stone, we just change the Angular framework. And the only thing that you need to do is to swap this dependency here, right? So I have an experimental fork of Angular that does trusted types, and that's it. I just pointed my application to use that one. And let's see what happens. Spoiler alert, nothing nice. So let me just refresh this. And it's supposed to work, but of course something is going on. Like, what is that? This is some text area X, like, oh, jQuery, of course. Like, this application is also using jQuery. Like, why do we even? Right? All right, this is blocking. Like, we can't do our job. Like, jQuery does something to the DOM in this particular example, just write some text area for whatever reason. All right, but we can fix this, you know how? Default policy. Haha. Let's just recompile this. And in the meantime, I can show you what the default policy actually looks like. So there's a default policy. And let's go maybe from the bottom. This default policy simply says, whenever someone wants to create a trusted script URL, a trusted script, something that matches eval and those kind of things, just like, don't allow it. No, I don't want eval. If anything wants to create a script URL, only allow, first of all, only allow something from the whitelist. I will show you the whitelist in a second. But also try to recover, like report something and allow something anyways, right? So have some amount of control. Like, what's this allowed scripts regex, regular expression? Well, that's this one, right? Oh, YouTube API does something, whatever. Like, it just loads something using a string, whatever, we can live with that. Now, whenever something wants to create a trusted URL, so a URL that is not for scripts, we just like look at the URL, it's okay, if it's HTTP or HTTPS, I'm fine with it, whatever. Like, no JavaScript, it's an equivalent of a CSP without unsafe inline, kind of. And for HTML, well, we just do the jQuery workaround. It turns out that jQuery just does two things here. First of all, it tries to use those constant payloads here, and also a payload that is mildly dynamic, but still doesn't cause any XSS issues. So we just only allow jQuery to work. And that's it. Now, how does it look like for you? It's quite small, but it still is a code smell, no? That's a good thing that it's a code smell, because the default policy is this ugly workaround that you need to live with. What does it promote? You changing your dependencies, or either fixing them upstream. It's easy, I actually also ported jQuery, but whatever. So you can, it promotes you using the dependencies that are trusted type compliant or written in an elegant way, like not speaking to the DOM if they do not need to, for example. So we have this default policy. Let's see the application in action. Yay, it works, right? And it's a fairly complex application. Like there's a lot of DOM interactions going on here. Like there's some search button, you can play some music. Yeah, that's probably won't play because the audio is not connected, but you get the point, right? It's all functional. Like that's all we needed to do for trusted types. But was it? Actually, not really. Like there's this thing here. Remember, we allowed for some script URLs. Like let's try to see what's actually happening here. Yeah, so at one point, oh, Google Analytics, oh, why don't you? Right, so as we can see, the application somehow is loading the Google Analytics. Now, thankfully, this is your policy is part of your program, so you can analyze it, debug it, like developers do, right? Like just have a debugger interface and just like see what happens here. In this case, we can just explore the call stack. Oh, yeah, indeed, there's some string assignments to dynamically created script, and it's in the file that's Google Analytics something something. All right, let's go there. Yeah, that seems like a file. Now what's that thing here? Like, what's the squiggly line about? It's like, it looks like we're doing something wrong. All right, and there's this, the thing that disappeared. Yes, this thing. Oh, what is it? This resource URL assignment from strings, well, actually, that's here, might result in script execution and will trigger trusted type violation at runtime. Well, that's exactly what happened. Now, what is actually going on here? So, because trusted types is a type-aware API, right? We have types, not just strings. We can just write linter checks that are based on those types, are looking for are matching the things with the proper types, and just expect the right types to be assigned to the things, and warn the developer very early that they are doing something that probably is a bad idea. But not only that, we can just fix it. All right, so there's some magical function, and let's just import this function. Now I have no problem, we can save this and this would work, but I'm just wrapping something in a function that doesn't seem like it added any security whatsoever. Now, did it? Well, actually, it kind of did. If you take a look at this thing, this particular function is just using some literal script URL policy that seems unsecure because it also doesn't do any kind of validation, but the validation actually happens from the type annotations here. There's a bit of TypeScript magic. Thankfully, TypeScript has a pretty sane typing language, and what this typing annotation says is that this function should only be called with JavaScript string literals. That's it. If those are JavaScript string literals, they cannot possibly be controlled by the attacker. Let's see what would happen if I actually try to do that, right? Let's try to do location href here. That's clearly a DOM XSS. But what's going on here? Argument of type string is not assignable to a parameter of type not the string literal. Oh, shit. You know what actually happened? This application didn't compile. And of course, you can try to work around it a little bit. And at a certain point, you will, because, I mean, it's a linter, right? You can always confuse it. But the whole point of this exercise is that it makes writing secure code easy. So we can use, for example, this thing. Templated string is OK. But as soon as we try to interpolate something, it doesn't match the type, hence this red squiggly line. So this exemplifies how trusted types, by being a type-based API, can enable us to warn the developers very early in the process that they are doing something wrong, to embed security very early, not at runtime, but as you are writing the code, before even deployment. And that, I think, concludes the demo, at least. So, we've been doing trusted types for a couple of months now, very intensely. Trusted types as an idea has like maybe 2 years, but we only started working on it very recently. And what we see in our applications is that the DOM XSS string functions are not called too often. Usually you have some dependencies. Some of them, most of them are actually easy to migrate to trusted types. So you end up creating policies in a very few trusted components, like your templating library, a framework like Angular, like I showed, or the sanitizers. These areas of code are usually something that needs a policy. But that also means that everything else in your code base doesn't actually expose your application to the DOM XSS risk. You can just simply ignore it and pretend it doesn't exist. Well, you also have other vulnerabilities, so you should review it as well. But for DOM XSS, we kind of got it covered. There, of course, are a few misbehaving dependencies, as usual, like jQuery in the example. And the code size overhead of trusted types is really negligible. Like, literally, we have the polyfills because obviously we need to work with the browsers that do not yet implement the feature. So the tiniest of the polyfill, that's a little bit, it has some caveats, but it works, is 66 bytes of code. So fairly small. And we have ported our core JavaScript library used in Google and in a lot of applications called Google Closure. And there the overhead is 300 bytes for JavaScript binary. So fairly acceptable for DOM XSS assurance. We think that porting, especially modern applications, is quite easy. And we are already doing that in Google applications. We, again, ported the core JavaScript library to trusted types, and now we are working on enabling the trusted types through the header with some experiments on our main application development platform, let's say. Now, what's the project status? This API is available in Chromium browsers. So there's a couple of versions. We add new features, fix new bugs with every iteration. But it's available behind the flag, right? So you need to start Chrome with some command line flags. Unless you apply for the origin trial token, which enables you to test the application on a subset of your traffic, essentially, such that your customers, your users, do not have to, fiddle with the Chrome command line to have access to the API. We have a discussion group. There's a specification draft. There's lots of polyfills, documentations, and issues on our GitHub repository. This is the slide to make a photo of. And we are working actively on adopting trusted types in Google applications because we really, really are excited and see the benefits already of this approach. Of course, the crucial part is working on the external integrations, and this is something we are also pursuing. But again, we're just end developers, and we can't possibly fix every bit of the JavaScript ecosystem. So we need some help, obviously. We already ported the DOM Purify. We've added some type definitions to TypeScript such that you can start coding against this API fairly easily. We've made some trials with Angular applications. Here's a link to a sample patch that obviously wouldn't work from a photo, but the link to the slides will be the last one. We're looking at React, more frameworks to come. We are working on the secure policies libraries such that you don't have to figure out how to sanitize HTML on your own. You can just reuse our know-how in this area. And I think for the first time, we have actually a chance of addressing the DOM XSS problem after, 18 years, I think. It's not going to be like a one-stop solution, but I think it's a fairly reasonable one. Therefore, if I may do some call to action, try trusted types and let's end DOM XSS together. Thank you.
Thank you. Just one question.
All right. The question was, policies are created on a first-come, first-served basis. Will we see race conditions between secure and attacker-injected policies? How to prevent it? Yes, policies are created on the first, the first policy wins. So potentially you can have the race conditions. I don't think those would be race conditions with the attacker code actually, like the malicious code, because you don't have a foothold, right? If you are able to already execute the JavaScript code, then we already lost, and the DOM XSS is the least of your problems. You already have the code, you're already in, right? So what we might see is a developer creating or piggybacking on the policy name and trying to inject it earlier. But that's something that will just break at runtime pretty quickly, because your legitimate code will try to create the policy, 100 milliseconds later, and then the whole application will just break because of the type error. So it will be a pretty noisy error and not a good solution for, let's say, bypassing the security restriction your security team imposed on you. All right. Thank you.